Look at the clock nearest you. It keeps time. A ruler keeps distance. In your whole life, those two have never once traded places. They trade places constantly. Move faster through space and your clock runs slow, because the time you are handed and the distance you cross come out of one shared budget. This is Minkowski spacetime, a four-dimensional geometry in which space by itself and time by itself are shadows, and only their union is real. Think about what that claims. The place you occupy and the moment you are living are not two separate facts. They are two views of one fact, and the split between them shifts with how you move. In 1908, a mathematician named Hermann Minkowski stood before an assembly of scientists and said, "Space and time were doomed to fade into shadows." He was not being poetic. He had found the geometry. Here is what should stop you. For over a century, the finest experiments ever built have tried to catch space and time behaving as two independent things, and to about 1 part in a billion, they never have. One number binds every observer in the universe together, and it belongs to no one's clock and no one's ruler. Come with me. Start with the question the entire subject turns on. Suppose your clock and my clock disagree about how much time passed between two events, and your ruler and my ruler disagree about how far apart those events were. Is there anything at all left that we both measure the same? There is exactly one thing. It is not the time, it is not the distance. It is a specific combination of the two, and every observer in the universe, no matter how fast they move, computes precisely the same value for it. That combination is called the space-time interval, and it is the beating heart of everything that follows. Here is how it works, at a first honest level, before we bury it in mathematics. Imagine two flashes of light, a firecracker at the corner of a room and a second firecracker a moment later across the room. You, standing still, will measure some time between them and some distance between them. Now picture someone gliding through the room on a fast cart, passing you as the firecrackers go off. That moving observer measures a different time between the flashes and a different distance between them. Not because their instruments are wrong, because time and distance are genuinely not fixed quantities. They depend on the state of motion of whoever is measuring. So, what survives? Take the distance, square it. Take the time, multiply it by the speed of light, square that, and subtract it. What you are left with, that single number, is identical for you and for the moving observer. You disagree about the pieces, you agree exactly about this particular blend of the pieces. And the moment you see that, the old picture of a fixed stage of space with a separate clock ticking over it begins to come apart in your hands. Why should the pieces disagree in the first place? Because of a rule discovered before Minkowski ever drew his geometry. The rule that carries the name of the Dutch physicist Hendrik Lorentz. In the 1890s and early 1900s, Lorentz was wrestling with a stubborn experimental fact. Light seemed to travel at the same speed no matter how you chased it. To make the equations work, he wrote down a transformation, a recipe for converting one observer's measurements into another's. Henri Poincaré working in France, sharpened it and saw that it behaved like a rotation. And here is the recipe, stated so you can hear it. The moving observer's time equals gamma times the quantity your time minus your position times velocity over the speed of light squared. Their position equals gamma times the quantity your position minus velocity times your time. In symbols, t prime equals gamma times, open bracket, t minus v x over c squared, close bracket. And x prime equals gamma times, open bracket, x minus v t, close bracket. Gamma is 1 divided by the square root of 1 minus v squared over c squared. Let me translate every piece. The letter v is the relative speed between the two observers. The c is the speed of light, 299,792,458 meters per second, about 186,282 miles per second. And gamma is a stretch factor that sits at 1 when you are barely moving and climbs toward infinity as you approach light speed. Now look at what that transformation actually does. To find the moving observer's time, you take your time and mix in a piece of your position. To find their position, you take your position and mix in a piece of your time. Time bleeds into space. Space bleeds into time. There is no clean partition. What does it mean that you cannot write down where an event is without your answer depending on when, and cannot write down when without it depending on where? It means the wall between them was never real. It was a low-speed illusion, holding only because nothing in your daily life moves fast enough to expose the leak. Think about a currency exchange, because the analogy is exact and it will carry us a long way. Suppose you keep your wealth partly in dollars and partly in euros. A friend keeps the identical wealth but converts more of it into euros. If someone asks how many dollars you have, you and your friend give different answers. If they ask how many euros, different again. But your total net worth, converted through the honest exchange rate, is the same. Space and time are the two currencies. Different observers hold different amounts of each. The space-time interval is the net worth, the quantity that survives every conversion. The Lorentz transformation is the exchange rate. And the strange minus sign we will meet shortly is the one place where this currency behaves unlike any money you have ever handled. Does the mixing actually happen, or is it just bookkeeping? This is where a laboratory in Darmstadt, Germany, earns its place in the story. In 2014, a team including Benjamin Bottermann and Guido Sartoff, working at the GSI Heavy Ion Research Center, took lithium ions, lithium atoms stripped of an electron, and accelerated them in a storage ring called the ESR until they were moving at 33.8% of the speed of light. That is roughly 101,000 kilometers per second, about 63,000 miles per second. Then they used the ions themselves as clocks, reading the frequencies of light the ions absorbed and emitted. If time and motion through space are independent, a fast clock and a slow clock should tick alike. They do not. The moving ions' internal clocks ran slow, and they ran slow by exactly the amount the Lorentz factor predicts, verified to within 2.3 parts in a billion. Read that again. To 9 decimal places, motion through space stole from the passage of time, on the precise schedule Minkowski's geometry demands. This is the part that stays with me. Not the speed of the ions, the discipline of the number. Somebody could have built that ring, run those ions, and found a discrepancy in the 8th decimal place, and the whole edifice would have wobbled. Instead, the measurement landed dead on the line. When I first sat with that, I had to put the paper down for a while. So now we can write the invariant itself and give it the weight it deserves. The space-time interval squared equals minus the quantity speed of light times the time gap squared plus the distance gap squared in each of the 3 directions of space. In symbols, s squared equals minus, open bracket, c times delta t, close bracket, squared, plus delta x squared plus delta y squared plus delta z squared. Delta t is the time between 2 events. Delta x, delta y, delta z are the distances between them along the 3 spatial axes, and c is again the speed of light. This is the number the moving observer and the still observer both compute and both agree on. Minkowski wrote it down in 1908, and it is arguably the single most important equation in this entire subject, because it is the mathematical statement of the sentence in this video's title. Space does not exist on its own. Time does not exist on its own. This, their union, is what exists. Let me plant a seed here because we will return to it. Notice that one term in that equation carries a minus sign, while the other 3 carry a plus. 3 of space, 1 of time, and the time term flipped. Hold that minus sign in your mind. It is the smallest detail in the equation and the deepest mystery in the subject. And near the end, we will find that physics still cannot fully explain why it is there. For now, ask the practical question. If the interval is the real quantity, how do working physicists actually use it, not in philosophy, but at the bench, moving equipment and reading dials? The answer takes us from a storage ring in Germany to the largest machine humans have ever built. Beneath the border of France and Switzerland runs a circular tunnel 27 kilometers around, about 17 miles, called the Large Hadron Collider, operated by CERN. Inside it, protons are driven to very nearly light speed and smashed head-on, and enormous detectors called ATLAS and CMS record the debris. On the 4th of July 2012, those 2 detector teams announced they had found the Higgs boson. Here is the piece almost nobody explains. They did not see the Higgs. It vanishes in a fraction of a second, long before it could reach any detector. What they saw were its fragments, often 2 photons, sometimes 4 charged particles called leptons. So how do you find a thing you cannot see from only its pieces? You use the geometry. This is where 4 vectors enter, and they are simply the union idea applied to motion. A 4 vector packages energy and momentum into a single object, the way space-time packages time and space. The energy sits in the time-like slot. The three components of momentum sit in the space-like slots. And just as the space-time interval is the invariant length of a separation between events, there is an invariant length to this energy-momentum object. And that invariant length is mass. Every observer, in every state of motion, computes the same value for it. Hear the equation, because it is the collider's entire game. Energy squared equals, open bracket, momentum times the speed of light, close bracket, squared, plus, open bracket, mass times the speed of light, squared, close bracket, squared. In symbols, E squared equals pc squared plus mc squared squared. E is total energy. The P is momentum. The M is the invariant mass, the true frame-independent mass. And C, once more, is the speed of light. When physicists at ATLAS and CMS caught two photons flying out of a collision, they measured each photon's energy and momentum, added the four vectors together, and computed the invariant length of the sum. Do that for millions of collisions and plot the results, and most of the time you get random background. But at one specific value, near 125 billion electron volts, a bump rises out of the noise. That bump is the invariant mass of something that existed for an instant and then decayed. The combined result from ATLAS and CMS put it at 125.09 billion electron volts, give or take about 2/10. What does it mean that the most celebrated discovery in modern particle physics was, mechanically, an exercise in computing a space-time invariant? It means the union is not a philosopher's abstraction. It is the working tool of the people who find new particles. They do not measure mass with a scale. They reconstruct it from the geometry of four vectors, and it comes out the same in every laboratory on Earth, because it is an invariant. Picture a detective reconstructing a collision between two cars from the skid marks and the wreckage. Different witnesses, standing on different corners, saw different speeds and different angles. But the detective, combining the evidence correctly, recovers the one quantity all of them must agree on, the momentum that was there before impact. The collider physicist is that detective, and invariant mass is the quantity the whole universe is forced to agree on. Now let me give you the human story, because it is one of the strangest in the history of science, and it has been woven into the mathematics all along. Hermann Minkowski was born in 1864 in what is now Lithuania. He became a mathematician of the first rank, and in the late 1890s he taught at the Zurich Polytechnic. One of his students was a young man named Albert Einstein. Minkowski was not impressed. Years later, recounting his surprise to the physicist Max Born, he called Einstein a lazy dog who never bothered about mathematics at all. Then, in 1905, that lazy dog published Special Relativity and reorganized physics. Here is the turn. Einstein had written relativity as a theory about clocks and rulers, about measurements made in moving laboratories. It was, in the language of physicists, kinematic. It was Minkowski, the dismissive former teacher, who saw that all of it could be recast as geometry. In September of 1908, At a meeting of German scientists in Cologne, Minkowski delivered a lecture titled Raum und Zeit, Space and Time, and opened with a line that still gives me pause. The views of space and time he was about to present, he said, had sprung from the soil of experimental physics, and therein lies their strength. He declared that henceforth space by itself and time by itself were doomed to fade into mere shadows, and only a union of the two would preserve an independent reality. 4 months later, in January 1909, Minkowski was dead of appendicitis at 44. He never saw what his geometry would become. And what did it become? The indispensable scaffolding of Einstein's own next theory. Einstein at first grumbled that Minkowski's reformulation was needless mathematical decoration. Then he tried to build general relativity, gravity as the curving of space-time, and found he could not do it without exactly the geometric language Minkowski had handed him. The student's physics was rebuilt in the teacher's geometry, and the student came to depend on it completely. There is a deeper lineage here, and it is worth naming because it explains why Minkowski, of all people, saw what Einstein missed. Decades earlier, in 1872, the mathematician Felix Klein had proposed a radical way to understand geometry itself, the Erlangen program. Klein's idea was that you define a geometry not by its points and lines, but by the group of transformations that leave its essential properties unchanged. What is invariant under the group is what is real in the geometry. Minkowski had been steeped in this way of thinking. So when he looked at the Lorentz transformations, he did not see a bookkeeping trick for moving clocks. He saw a transformation group, and he asked Klein's question: what does this group leave unchanged? The answer was the interval. In one stroke, the physics of relativity became the geometry of a four-dimensional space, whose real content is whatever the Lorentz group preserves. The invariants became the physical objects. Think of it as the difference between a photographer and a cartographer. Einstein had photographed reality from many angles and noticed the photographs disagreed. Klein had taught that the map is defined by what stays fixed as you turn it. Minkowski drew the map. We have the mechanism now, and we have the people. So let us go deeper into the feature of this geometry that is genuinely unlike anything in ordinary experience: that single, stubborn minus sign. In the geometry you learned in school, distances are built by adding squares. The diagonal of a rectangle is the square root of the width squared plus the height squared. Rotate your coordinate axes and the width and height of a given line change, but the diagonal, the true length, stays fixed. That is Euclidean geometry, and every term is a plus. Minkowski's geometry looks almost identical, with one violent exception. The time term enters with a minus. Physicists write the rule for it as the metric, and it comes in two conventions that fight a low-grade war in the literature to this day. One camp writes the signature as minus plus plus plus. They call it mostly plus, or the East Coast Convention, and it dominates in general relativity, string theory, and formal field theory. The other camp writes plus, minus, 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 the mostly minus, the West Coast convention, favoured by particle physicists. It is the same geometry either way, only the sign bookkeeping differs. But both camps agree on the one thing that matters. Time and space carry opposite signs. The war between them fell, yes, but they did not merge into sameness. They merged into a union with a twist built into its very metric. What does that minus sign actually do to the world? It reverses the logic of distance for anything separated in time. In ordinary space, a straight line is the shortest path between 2 points. In space-time, for a traveller moving between 2 moments, a straight world line, the path of someone left alone, unaccelerated, is the path of maximum elapsed time, not minimum. The one who takes the long, curving, accelerated route through space logs less time on their own clock. This is the geometric root of every time dilation result physics has ever measured. It is not that motion damages clocks, it is that the geometry assigns less proper time to the longer spatial path, exactly because of the flipped sign. Picture 2 hikers crossing the same valley. In ordinary hiking, the one who wanders takes longer. In Minkowski's valley, the one who wanders ages less. The minus sign turned the arithmetic of experience inside out. Consider what this means for how physics measures time itself. The quantity a moving clock actually reads is called proper time, and it is tied directly to the interval. Proper time squared equals the negative of the interval squared, divided by the speed of light squared. Work it through, and it reduces to a clean statement. The time your clock reads equals the coordinate time multiplied by the square root of 1 minus your speed squared over light speed squared. Move, and that square root drops below 1. Your clock reads less. The GSI ions we met earlier were a direct measurement of that square root, confirmed to 9 decimal places. So, proper time is not a universal river. It is the length of your particular path through the geometry. And the geometry, because of that minus sign, makes the straight and lazy path the longest of all. Before I continue, take a moment with that. The most restful thing you can do, nothing at all, drifting unaccelerated through space, is, in the currency of your own lifetime, the most expensive path available. Doing nothing buys you the most time. Sit with that for a beat, because our language has no comfortable place to put it. Now, the minus sign does something even more consequential than reshaping clocks. It carves the universe into regions of possible and impossible influence, and it does so purely as geometry. This is the light cone, and it is one of the most beautiful structures in physics. From any event, any here and now, draw the paths that light would take, forward and backward. Those paths form a cone in space-time. Everything inside the forward cone is your possible future. Events you could still reach or influence, because a signal from you, travelling at or below light speed, could get there. Everything inside the backward cone is your possible past, events that could have influenced you. And everything outside both cones is a vast region physicists call elsewhere. Events so far away in space and so close in time that no signal, not even light, could connect you to them. You cannot affect them. They cannot affect you. They are causally sealed off. Where does the cone's boundary come from? Straight from the interval. When the interval between two events is exactly zero, the equation says the speed of light term precisely cancels the distance term, which happens only for something moving at light speed. That zero interval surface is the cone. Inside it, the interval is what physicists call time-like, and cause can reach effect. Outside, the interval is space-like, and no influence can cross. What does it mean that causality, the entire order of what can affect what, is written into the geometry of space-time and needs no reference to light bulbs or radio waves at all? It means that the structure of cause and effect is not a fact about electromagnetism. It is a fact about the shape of the union. Light happens to travel on the boundary, but the boundary would be there even in a universe with no light in it. Think of it as the physics of a shout in a crowd. If you shout, the sound spreads outward at a fixed speed. Anyone it has already reached could, in principle, be reacting to you. Anyone it has not yet reached cannot possibly be responding to this particular shout. They are, for now, in your elsewhere. The light cone is that idea made absolute and made geometric, with the speed of light as the one shout that nothing can outrun. This raises a question that has troubled careful thinkers for a century, and I want to handle it precisely because a companion film on this channel has already explored one branch of it in depth. If different observers slice space-time differently, if there is no universal agreement on which distant events are happening now, then what happens to the idea of a single, shared, present moment across the universe? The physicist N. David Mermin put the lesson as sharply as anyone, that no inherent meaning can be assigned to the simultaneity of distant events is, he wrote, the single most important lesson to be learned from relativity. Roger Penrose dramatized it with two people walking past each other on a street who, doing the geometry honestly, assign different nows to events in the distant Andromeda galaxy. And that thread, the collapse of the universal present into a personal one, is the subject of another film here, so I will not re-walk it. I raise it only to mark the boundary it sets. Relativity does not merely bend time, it denies that there is one time to bend. The present is a local affair, and it cannot be stretched into a universe-wide sheet. But notice, and this is the part too rarely stressed, the light cone rescues something the loss of universal time seemed to threaten. Even though observers disagree about which distant events are simultaneous, they never disagree about causal order. If one event is inside another's forward light cone, every observer agrees which came first. Cause always precedes effect for everyone. The disagreement about now is confined entirely to the causally sealed elsewhere, where it can do no harm, because nothing there can influence anything here. What does it mean that the universe will let observers argue endlessly about simultaneity, but never about cause and effect? It means the geometry is protecting something. It permits disagreement precisely where disagreement is harmless, and forbids it exactly where it would break the world. That protection has a name in the most rigorous formulation of quantum field theory, and it leads us into territory the other films on this channel have not touched: the strange, saturated emptiness of the vacuum. In the 1960s, working to put quantum field theory on a firm mathematical footing, Rudolf Haag and Daniel Kastler built a framework in which you assign to every region of spacetime the collection of physical measurements you could perform inside it. One of its axioms is called microcausality. Any two measurements made in regions that are space-like separated, outside each other's light cones, must commute. In plain language, performing one cannot disturb the outcome of the other. It is the light cone's law of causality, translated into the grammar of quantum mechanics. And it is what guarantees that quantum entanglement, spooky as it is, can never carry a usable signal faster than light. Inside this framework sits one of the most astonishing theorems in physics, proved in 1961 by Helmut Rey and Siegfried Schlieder. It says that the vacuum, empty space, the state with nothing in it, is so thoroughly threaded with correlations that by performing operations confined to any tiny region of space, however small, you can approximate any state of the entire universe arbitrarily well. Let that sink in. Manipulating the field in a region the size of a grain of sand can, in principle, reproduce a configuration describing distant galaxies. The vacuum is not empty in the sense of being featureless. It is entangled everywhere with everywhere. Picture a vast library in which every small alcove secretly contains a coded imprint of the entire collection, so complete that a reader confined to one alcove could, with the right procedure, reconstruct any book in the building. That is the Rey-Schlieder vacuum. And here is the objection you should be forming right now, because it is the correct one. If a local operation can reach the whole universe, doesn't that let me send a message faster than light? The answer is no, and the reason is microcausality. You can reproduce a state, but you cannot transmit a choice. Anything you do in your region commutes with any measurement in a space-like separated region, so no one over there can detect that you did anything at all. The entanglement is real, the signal is impossible. What does it mean that empty space is simultaneously saturated with correlation and utterly incapable of carrying a message across it? It means the union polices itself. The very geometry that permits the entanglement forbids its abuse. We have tested that prohibition directly, and the tests are among the cleanest experiments ever performed. In 2015, 3 groups, one in Delft using nitrogen defects in diamond separated by 1.28 kilometers, one in Vienna using entangled photons, one at the American Standards Laboratory, NIST, with detectors 185 meters apart, closed the last loopholes in what is called Bell's theorem. They confirmed that entangled particles are correlated more strongly than any picture of separate, independent local objects allows, and confirmed at the same time that those correlations transmit nothing. Both halves are true at once. The particles are more deeply joined than classical intuition permits, and the joining respects the light cone absolutely. The union holds even in the quantum vacuum. Now, let me show you the other face of this geometry, the one where physicists deliberately take the union apart, on purpose, because they have to in order to compute. Because a fair account of space and time are one must confront a fact that looks like a contradiction. Every simulation of colliding black holes ever run has begun by splitting space-time back into space and time. How can that be if the split is not real? The tool is called the ADM formalism, after Richard Arnowit, Stanley Deser, and Charles Meisner, who developed it in the late 1950s and early 1960s. It rewrites the geometry of space-time as a stack of purely spatial slices, each one a three-dimensional snapshot evolving forward through a time parameter. The recipe introduces two new objects with wonderfully concrete names. The lapse function, written alpha, tells you how much proper time actually elapses between one slice and the next, how fast real clocks tick as you climb the stack. The shift vector, written beta, tells you how the spatial coordinates get relabeled from one slice to the next, how the grid slides sideways as you go up. The line element in this language reads interval squared equals minus lapse squared times coordinate time squared plus the spatial metric contracted with the coordinate steps, each corrected by the shift. In symbols, physicists write ds squared equals minus alpha squared dt squared plus gamma ij times the quantity dxi plus beta I dt times the quantity dxj plus beta j dt. The gamma here is the geometry of each spatial slice. This is the framework that lets scientists at LIGO's supporting theory groups simulate the 2015 merger of two black holes and predict the gravitational wave signal before the detectors caught it. Here is the crucial point, and it is the resolution of the apparent contradiction. The lapse and the shift are choices. They are not dictated by nature. Relativists have a saying, the art of numerical relativity is the art of choosing the lapse and shift wisely. Pick them one way, and your slices tick fast here, slow there. Pick them another way, and the grid flows differently. The physics, the gravitational waves that come out, the invariant interval between any two events, is identical no matter how you slice. So, the ADM split is real the way slicing a loaf is real. The loaf permits infinitely many slicings, and the bread is indifferent to which one you choose. What does it mean that we can cut space-time into space and time in endlessly many ways and always recover the same physics? It means the cut is ours, not nature's. The union is the loaf, the slices are our knife work. And the fact that the knife can fall anywhere is the strongest evidence that no particular cut is built into reality. That word, wisely, should raise a question, though. And it is the question that opens the deepest debate in the whole subject. If the split into space and time is merely a convenient choice with no physical content, then why do some serious physicists believe there might be a preferred way to slice after all? A true physical division between space and time hiding underneath the union. To take that question seriously, we have to look at the frontier where relativity meets the quantum, and at the experiments quietly trying to catch the union in a lie. For over a century, physicists have hunted for any crack in Lorentz invariants, any sign that space has a preferred direction, or that time and space are not perfectly interchangeable under a boost. The modern search has a common language, built in 1997 and 1998 by Don Collider and V. Alan Kosteletsky. It is called the Standard Model Extension, and its strategy is simple and ruthless. Take the entire standard model of particle physics and add to it every conceivable term that would violate the Lorentz symmetry, each tagged with a coefficient measuring how strong the violation is. Then send experimenters out to measure those coefficients. If the union is exact, every coefficient is 0. Kosteletsky and Neil Russell maintain a running catalogue, the data tables for Lorentz and CPT violation, updated roughly every year. The edition current, as of early 2026, runs to nearly 200 pages of bounds across matter, light, neutrinos, and gravity. And the verdict, written across all those pages, is the same: consistent with 0, everywhere. The framework's honest weakness is that it detects nothing on its own. It only gives null results a common yardstick. But what a yardstick it is! How tight are the bounds? Return to Berlin. In 2015, Moritz Nagel, Stephen Parker, Michael Tobar and their colleagues took cryogenic sapphire resonators, crystals cooled to near absolute zero, in which microwaves ring like a struck bell, mounted them on a rotating platform, and watched for any change in the ringing frequency as the apparatus turned to face different directions in space. If space had even a faint grain to it, a preferred axis, the frequency would wobble as the crystals swung around. It did not. They constrained any such directional dependence to 9.2 plus or minus 10.7 parts in 10 to the 19th power. That is the 1 part in a billion billion from the very start of this film. It is the modern descendant of the famous 1887 experiment by Michelson and Morley, which first failed to find a preferred frame and helped launch the whole revolution. Except that where Michelson and Morley reached a precision of parts in 10,000, the sapphire resonators reach parts in 10 quintillion. What does it mean that a century of ever finer instruments, straining to catch space showing a preferred direction, has caught precisely nothing to 18 decimal places? It means that if the union is an approximation, the deeper truth it approximates is hidden with a thoroughness that itself demands explanation. There is one more thread to lay down before we begin to weigh, and it is the loose one, the single live anomaly that keeps this subject from being closed. It concerns not local physics, but the universe as a whole. When we look out at the cosmic microwave background, the faint afterglow of the early universe filling all of space at a temperature of 2.725 Kelvin, it is not perfectly uniform. One side of the sky is very slightly warmer, the opposite side very slightly cooler, by about 3.36 thousandths of a Kelvin. This is called the CMB dipole, and the standard reading is that it is a Doppler effect. Our whole solar system is moving through the universe at about 370 kilometers per second, precisely 369.82 kilometers per second, measured by the Planck satellite. And that motion warms the sky ahead and cools the sky behind. The relation is captured by a clean formula. The observed temperature in a given direction equals the base temperature times the square root of 1 minus beta squared divided by 1 minus beta times the cosine of the angle, where beta is our speed as a fraction of light speed. To first approximation, the sky brightens by a factor of 1 plus beta times the cosine of the angle in the direction of motion. That would be a tidy story, our motion, and nothing more. Here is the crack. If the dipole is purely our motion through space, then a completely different measurement should agree with it, counting distant galaxies and quasars across the sky. Move through a uniform sea of them, and you should see slightly more ahead than behind, by an amount the same motion predicts. In 2021, Nathan Seacrest and collaborators counted 1,355,352 quasars from the infrared Catwise survey and measured exactly that kind of dipole. But it came out more than twice as large as our known motion predicts. The odds of that being a fluke, they reported, were about 1 in 2 million, a 4.9 sigma result. Follow-up work only sharpened the tension. Combining radio and infrared surveys pushed it to 5.1 sigma. A Bayesian reanalysis in 2023 reported 5.7 sigma. A combined radio study in 2025 found the dipole nearly 4 times too large at 5.4 sigma. Hold that discrepancy in your mind. We will return to it, because it is the one piece of evidence that could, if it survives, force us to revise the grandest version of our story. For the past hour, we have laid out what the evidence shows. We built the union from the interval, watched space and time mix under the Lorentz transformation, confirmed the mixing in a German storage ring, reconstructed a new particle from 4 vectors beneath the French-Swiss border, felt the weight of the minus sign, mapped causality onto the light cone, found the vacuum saturated with harmless entanglement, watched relativists slice the union apart at will, and pushed the search for a crack to 18 decimal places. Now we do the harder thing. Now we weigh the competing scientific explanations of what all this means, and we say plainly which one the evidence supports and where, honestly, the road runs out. There are 3 explanations on the table, and I will state each in its strongest form before judging any of them, because a resolution reached by caricaturing the alternatives is worth nothing. The first is the mainstream position. The union is fundamental at every energy we can reach, and there is no preferred frame, no true physical division between space and time hiding underneath. Space alone and time alone are frame-dependent shadows. The interval and the 4 vector magnitudes are the frame-independent reality. What is the evidence for it? Nearly everything we have touched. the sapphire resonators finding no preferred direction to 1 part in 10 quintillion, the GSI ions confirming time dilation to 9 decimal places, the entire Collider program, whose every reconstructed mass is a Lorentz invariant computed identically in every laboratory, the Kosteletsky-Russell tables, 200 pages of coefficients, all consistent with 0. Does this explanation actually fit the evidence? On local physics, physics done in a lab, in a region small enough to ignore the expansion of the universe, it fits with a completeness that is almost unnerving. Where does it fall short? It is silent on 2 questions it does not even pretend to answer. What happens to the union at the enormous energies of quantum gravity near the Planck scale, where space-time itself may fray? And why the metric is Lorentzian? Why there is 1 minus sign rather than Euclidean with 4 plus signs? It describes the union flawlessly. It does not explain why the union has the shape it does. The second explanation says the split into space and time is not merely our convenient knife work, that at high enough energy there is a true, physically preferred slicing, and the union we measure is only what emerges at low energy. The boldest version is Hosava-Lifshitz gravity, proposed by Peter Hosava in 2009. Hosava was blunt about his motive. "I'm going back," he said, "to Newton's idea that time and space are not equivalent." His theory lets space and time scale differently. You can stretch time by 1 factor and space by another, with a mismatch measured by a number called the dynamical critical exponent, which equals 3 at high energy and relaxes to 1, the relativistic value, at the low energies we inhabit. Why do that violence to the union? Because it may cure one of the deepest technical diseases in physics, the failure of gravity to behave sensibly as a quantum theory. Hosava's anisotropic scaling makes gravity power counting renormalizable, mathematically tame in the ultraviolet, a prize that has eluded physicists for generations. A related program, Shape Dynamics, developed around 2010 to 2013 by Julian Barber, Sean Gribe, Tim Kozlowski, Enrique Gomez and Flavio Mercati, makes a different trade. It is dynamically equivalent to Einstein's gravity, but it swaps the freedom to re-slice space-time for a different symmetry, the freedom to rescale sizes locally in space. Its authors argue it dissolves the notorious problem of time in quantum gravity by making a preferred notion of simultaneity physical rather than arbitrary. Does the second explanation fit the evidence? Here we must be scrupulous. As theoretical machinery, these are serious, motivated programs, and the problem they attack, reconciling the union with the quantum, is real and unsolved. But as claims about the world we measure, they face a wall. Every experiment we have described disfavors a physically preferred local frame. The resonators would have seen the grain. They saw none. Hosava's original theory, moreover, suffers from internal troubles, a stubborn extra mode and strong coupling problems that its healthier descendants only fix by adding structure. And the modified way it would make gravitational waves travel is constrained by real observations, including the near-simultaneous arrival of light and gravitational waves from the neutron-star merger observed in 2017. So where does explanation 2 stand? as a live minority research program aimed at the quantum gravity frontier, entirely legitimate. As a description of the space and time we can currently measure, unsupported, because the preferred slicing it needs has left no fingerprint anywhere we have looked. The third explanation is the subtlest, and it is the one riding on that quasar anomaly we set aside. It says, local physics may be perfectly Lorentz invariant, with no preferred frame in any laboratory, and yet the universe as a whole may still single out a rest frame. The cosmic microwave background does define one. There is a state of motion in which the afterglow looks most uniform, and our 370 km/s drift is measured against it. That by itself breaks nothing. A global rest frame set by the average matter of the cosmos is fully compatible with local Minkowski geometry, the way a preferred downhill on a landscape does not violate the fact that geometry is the same at every point. But the quasar dipole, if it is real, says something sharper, that the frame picked out by counting galaxies disagrees with the frame picked out by our motion at better than 5 sigma. If that holds, the cosmological principle, the assumption that the universe looks the same in every direction on the largest scales, is in trouble. And the tidy picture of a single kinematic rest frame is incomplete. Does explanation 3 fit the evidence? This is where forensic honesty matters most, because the temptation is to reach for the exciting reading. The anomaly is statistically strong, 4.9 to 5.7 sigma, across several independent analyses by Seacrest, Dam, Wagenveld, Boehmer and others. But strength is not the same as security. Skeptics, von Hausegger, Abgari, Mittal and colleagues, have identified plausible ways a survey could manufacture such a dipole. Subtle biases tied to the ecliptic plane, contamination from higher-order structure in the source distribution, differences in how surveys are calibrated across the sky. And crucially, at least one independent quasar sample, called Quire, recovers a dipole consistent with the standard motion, no anomaly at all. So the third explanation sits in genuine suspension. It is not confirmed, it is not dismissed. It is the one live data point in this entire field that, if it survives another decade of scrutiny, would force a real revision, not of local Minkowski geometry, which remains untouched, but of our assumption that the cosmos hands us only one purely kinematic rest frame. So now the weighing resolves. Which explanation does the evidence support? On the central question this film set out to answer, do space and time exist independently or only in union, the verdict is not close. The first explanation carries the day overwhelmingly at every energy and every scale we can currently probe. The claim that space alone and time alone are separately real, separately invariant things is not merely incomplete, it is disproven, and disproven to 18 decimal places by the resonators, to 9 by the storage ring, and reconfirmed in every particle mass ever reconstructed at a collider. What survives every measurement is the union, the interval, the 4 vector, the light cone, the invariant mass. Space and time as independent stages were the illusion. Their union is the reality the instruments keep finding. Now let me return to the threads I asked you to hold and tie them off honestly, because a resolution that hides its loose ends is a sermon, not science. The first thread was that minus sign, the flipped sign on the time term that makes the whole geometry Lorentzian instead of Euclidean. Here is the honest state of things. Physics can tell you with total precision what the minus sign does. It builds the light cone. It orders cause and effect. It makes the lazy path the longest lived. It gives mass its meaning as an invariant length. What physics cannot yet tell you is why the sign is there at all. Why the universe's geometry is built with one time-like direction opposed to 3 space-like ones, rather than 4 alike. That is not a question we are close to answering. It is a question we do not know how to ask properly. What does it mean that we can compute every consequence of a feature whose origin we cannot explain? It means our knowledge of the union is deep in its workings and shallow at its root. And it is more honest to say so than to dress the gap in confident language. The second thread was the tension between the local and the global. No preferred frame in any laboratory, yet a cosmic rest frame written across the sky, and a quasar anomaly hinting the cosmic story may be more complicated than a single drift. That tension is unresolved, and it is unresolved in the productive way, the way that keeps a field alive. It does not threaten the union of space and time. Local Minkowski geometry stands regardless of how the dipole debate settles. What is at stake is subtler and grander. Whether the universe as a whole is as even-handed in every direction as we have assumed. The next decade of surveys will decide it. For now, the correct posture is neither excitement nor dismissal, but patience. And that brings us to the deepest thread of all, the one this channel has circled before and will circle again, and the one where I have to be most careful to tell you exactly what the science does and does not settle. We have established, beyond serious doubt, that space and time do not exist on their own, that the union is what every measurement finds. But is that union itself the bottom layer of reality? Or does it, too, emerge from something deeper, some pre-geometric structure in which neither space nor time nor their union yet exists, and out of which all three condense the way temperature emerges from the jostling of atoms that have no temperature of their own? Here I must say plainly what the evidence can and cannot reach. Every experiment we have discussed probes the union from inside it. The resonators, the ions, the colliders, the Bell tests, all of them are performed within spacetime, using spacetime. And they can tell us with staggering precision that the union is exact at the scales we can touch. What they cannot do is step outside the union to see whether it rests on something else. That question, whether Minkowski's geometry is the foundation or merely a very good floor over a deeper cellar, lives at the frontier where quantum gravity is being built, in programs this channel has explored elsewhere. And it is not settled by anything in the present evidence. The honest sentence is this: the union survives every measurement we can make. And whether the union is fundamental or emergent is a question our instruments cannot yet reach. I will not close that door with a confident answer in either direction, because the science does not license one. Here the road genuinely runs out, and it is more truthful to stand at its end and look than to pretend it continues. This is the point I return to most often. Not the precision of the resonators, remarkable as it is, the edge. We have built a picture of reality so exact that it predicts a particle's mass to a fraction of a percent by adding up geometric vectors. And that same picture, pressed on the question of its own foundation, goes quiet. There is something bracing in a science, confident enough to say, this far and no farther. Not yet. The old picture the union replaced was not vague intuition. It was a precise, respected geometry in its own right. And to feel the weight of what Minkowski did, you have to see exactly what he overturned. Isaac Newton's universe had a spacetime too, though nobody called it that. Physicists now name it Galilean spacetime, and its rule for combining measurements is the one your body still believes. In Galilean spacetime, time is a single universal coordinate stacked on top of three-dimensional space. And when you change from one moving frame to another, the positions shift, but the clock is untouched. Add your walking speed to the train's speed, and you get your speed over the ground. The times simply agree. That is the Galilean transformation. And it is not wrong so much as it is a limit, the shape Minkowski's geometry collapses to when every speed involved is a crawl compared to light. What does it mean that the physics of your entire lived experience is a low-speed approximation to a geometry you never directly perceive? It means your intuition is not lying to you. It is reporting accurately on a corner of reality so slow that the union's twist never shows. The corner is real. The mistake is believing the corner is the whole room. The mathematical fingerprint of the difference is a single quantity. In Galilean spacetime, time intervals are invariant. Everyone agrees on how much time passed. And, separately, spatial distances between simultaneous events are invariant. Two invariants, one for time, one for space, cleanly divorced. In Minkowski spacetime, there is only one invariant, the interval, and it welds the two together with that flipped sign. Henri Poincaré, working in 1905 and 1906, saw the welding before almost anyone. He noticed that if you treated time not as t, but as an imaginary quantity, the speed of light times time, multiplied by the square root of -1, then the Lorentz transformation looked exactly like an ordinary rotation in a four-dimensional space, and the awkward minus sign vanished into the bookkeeping. Poincaré's trick, writing the time coordinate as ICT, was a piece of mathematical sleight of hand that made spacetime look Euclidean. Modern physicists have largely abandoned it because it hides the very thing that matters, the genuine physical difference between time-like and space-like directions. But it was the first glimpse that a boost is a rotation. Think of it this way. When you turn a photograph on a wall, its height and width trade off. A portrait tilted becomes partly wide, partly tall, but its diagonal never changes. Poincaré saw that a Lorentz boost turns a picture in which one of the axes is time. Speeding up does to your time and space what tilting does to a photograph's height and width. The interval is the diagonal that turning cannot touch. That word, rotation, points to the deepest organizing idea in the entire subject, and it deserves to be named directly because it ties everything together. The Poincaré group. When Minkowski asked Felix Klein's question, what transformations leave the interval unchanged? The full answer is a collection of 10 distinct symmetries. You can shift your origin in time, that is 1. You can shift it in each of the 3 directions of space, that is 3 more. You can rotate your spatial axes about any of 3 directions, 3 more. And you can perform a Lorentz boost along any of the 3 spatial directions, the final 3. 10 symmetries in all, and together they form the Poincaré group, the complete symmetry group of flat spacetime. Every conservation law you learned in school hangs from one of these symmetries. Energy is conserved because the laws do not change when you shift the time origin. Momentum is conserved because they do not change when you shift in space. Angular momentum is conserved because they do not change when you rotate. What does it mean that the great conservation laws of physics are not separate rules, but consequences of the symmetries of the union? It means the union is not a passive backdrop against which physics happens. Its symmetries dictate what physics is allowed to do. The stage writes the rules of the play, not by choosing them, but by its shape. Consider how much rides on the boost part of that group when physicists actually collide particles. Because there is a layer here, even most careful accounts skip. When 2 protons meet head-on inside the Large Hadron Collider, physicists want to describe the collision in a way that does not depend on who is watching or how the laboratory happens to be moving. They do it with quantities invented by Stanley Mandelstam in 1958. The Mandelstam variables, written S, T, and U. Each is built by adding or subtracting the 4 momenta of the incoming and outgoing particles, and taking the invariant length of the result. The variable S is the squared total energy available in the collision's own rest frame, the center of mass energy, the number that tells you how heavy a new particle you can afford to make. And here is the elegant constraint that binds them. S plus T plus U equals the sum of the squared masses of the 4 particles involved. 3 frame-dependent looking collisions, 3 invariant descriptions, locked together by 1 equation. When a physicist at Atlas says the LHC runs at 13 trillion electron volts, they are quoting the square root of S. It is a space-time invariant. The entire vocabulary of high-energy collisions is written in the invariants of the Poincaré group, because those are the only quantities every observer will agree on. And if your theory's predictions depended on the observer, it would not be physics. There is a companion idea at the collider that turns the union into a detective's tool for finding the invisible. And it is one of the most beautiful applications of 4-vector conservation in all of experimental physics. Neutrinos, and any hypothetical particles that do not interact with the detector, leave no track and deposit no energy. They fly out unseen. How do you measure something that refuses to be measured? You use conservation. Before the collision, the two protons are moving straight along the beam pipe, so their combined momentum sideways, transverse to the beam, is zero. Momentum is conserved. It is a component of a conserved 4 vector. So, after the collision, the transverse momenta of everything produced must also add to zero. Physicists add up the sideways momentum of every particle they can see. If the sum is not zero, if there is a lopsided push in one direction with nothing visible to balance it, then something invisible carried the missing momentum away. They call it missing transverse momentum, and it is how experiments infer the presence of neutrinos, and how they hunt for particles no one has ever detected. What does it mean that we routinely measure the momentum of particles we cannot see, purely by demanding that a space-time conservation law hold? It means the union is not only what survives measurement, it is what lets us measure the unmeasurable. The books must balance, and the balance reveals the ghost. Picture an accountant auditing a company whose ledger must sum to zero. Every visible transaction is entered, and the columns are added. If the total comes out short by a specific amount, the accountant does not conclude that money vanished. She concludes that a transaction happened off the books, and she knows its exact size and direction from the imbalance alone. The collider physicist is that accountant. The requirement that 4 momentum be conserved is the rule that the ledger must balance. And the neutrino is the off-book transaction, its properties reconstructed entirely from what is missing. This is invariants doing forensic work. Now let me widen the lens from the flat geometry to its curved relatives, because Minkowski spacetime does not stand alone. It is the flat member of a whole family, and naming its siblings shows why it matters so far beyond the laboratory. When Einstein built general relativity, he needed spacetimes that curve, and the mathematical objects he reached for are called Lorentzian manifolds, geometries that look like Minkowski spacetime in any small enough patch, the way the curved surface of the Earth looks flat in any small enough field. The signature, that 1 minus sign against 3 pluses, is preserved everywhere, even as the geometry bends. And within this family sit specific solutions with names worth knowing. There is de Sitter spacetime, the geometry of a universe driven apart by a positive cosmological constant, the shape our own universe seems to be approaching as its expansion accelerates. There is anti-de Sitter spacetime, its mirror image with a negative constant, which has become the theorist's favorite laboratory for quantum gravity. And there is the FLRW metric, named for Friedmann, Lemaitre, Robertson and Walker, the geometry of an expanding uniform cosmos, the working model of the Big Bang. Every one of these is a Lorentzian manifold. Every one carries the union's minus sign into its very definition. What does it mean that the shape of the entire cosmos and the frontier tools of quantum gravity are all built on the same time-like versus space-like distinction Minkowski drew in 1908? It means the union is not one theory among many. It is the grammar in which all the theories of spacetime are written. That grammar is exactly what the alternative theories proposed to rewrite. And having weighed them once, it is worth seeing precisely how radical the rewrite would be, how they treat time and space unequally on purpose. Return to Hosava's anisotropic scaling, and let me give it to you as an equation you can hear, because the structure is the whole point. Under Hosava's rule, if you zoom out by a factor, space stretches by that factor, while time stretches by that factor raised to a power called z. In symbols, time transforms as t goes to b to the z times t, while space transforms as x goes to b times x. When z equals 1, space and time stretch alike. That is the relativistic Minkowski case, the union intact. But Hosava sets z equal to 3 at the highest energies. Time and space scale by wildly different amounts. The union is deliberately broken at the smallest scales, on the bet that this is the price of making gravity a sensible quantum theory, and that the union we measure re-emerges as z flows back to 1 at the energies we inhabit. Think of a photograph, edited with a tool that stretches height and width by different amounts. A face pulled tall and thin. Hosava's universe applies that unequal stretch to space and time themselves, at scales far too small to have ever been probed. The claim is testable in principle. An unequal scaling of space and time would change how gravitational waves of different frequencies travel. So far, the observations, including the near-simultaneous arrival of light and gravitational waves from the 2017 neutron star merger, leave no room for it at the scales we can reach. The union, once again, holds where we can look. Let me draw out one consequence of the light cone that we have not yet followed to its end, because it reframes what causality even is. The condition for the boundary of the cone is the null interval, when the interval equals 0. Write it plainly. The interval is null when the speed of light times the time gap squared exactly equals the sum of the squared spatial gaps. In symbols, c squared delta t squared equals delta x squared plus delta y squared plus delta z squared. This is the surface where the time-like and space-like contributions perfectly cancel, and it is the path light itself travels. But here is the strange thing that falls out of it. For anything moving exactly at light speed, the interval along its entire journey is 0. A photon leaving a star 2,000 light-years away, crossing the void for 2,000 years by your clock, experiences an interval of exactly 0 between emission and absorption. In the geometry's own accounting, no proper time elapses for it at all. What does it mean that light, which defines the boundary of all causation, logs no time on its own journey? It means the minus sign has a razor's edge, and light rides precisely along it, the one path where the budget of space and the budget of time cancel to nothing. The photon does not experience the crossing as a duration. In the union's own bookkeeping, emission and absorption are, for the light, adjacent. This is the sort of result I find I cannot fully absorb in one sitting. The starlight entering your eye tonight, having crossed distances that stagger the imagination, carries in its own frame no record of any passage of time whatsoever. It is as fresh to itself as the instant it left the star. Take a moment with that before we move on, because our ordinary words, journey, travel, arrival, quietly fail here, and it is worth noticing exactly where they fail. The relativity of simultaneity, the fact that observers disagree about which distant events are happening now, has a precise and beautiful expression in the geometry. And while a companion film has traced its consequences for the nature of the present, the mechanism itself belongs here, in the story of the union, because it is the union's most direct, visible signature. When you change your state of motion, the set of events you consider simultaneous, your slice of now across all of space, tilts. Speed up in one direction, and the slice pivots. Events far ahead of you slide into your past. Events far behind slide into your future. The tilt is tiny for everyday speeds and enormous over cosmic distances, which is why two people strolling in opposite directions can, doing the geometry honestly, place a distant event days apart in time, while agreeing perfectly about everything in their own vicinity. The offset grows with distance because the tilt is an angle, and an angle spans more the farther out you go. What does it mean that simply changing your walking direction resorts which distant events you count as already happened? It means the slicing of the union into space now and time elapsed is not a feature of the world, it is a feature of your motion. Nature does not hand you a slice, you cut one by moving, and someone moving differently cuts a different one, and the loaf, the union, is indifferent to both. There is a subtle, honest point here that separates good physics from overreach, and the philosophers of physics Howard Stein and Stephen Savitt have pressed it carefully. The relativity of simultaneity tells you that a global now, a single slice spanning the whole universe that everyone must accept, has no invariant meaning. It does not, by itself, tell you what is metaphysically real about past, present, and future. That further step is contested, and it is the territory of another film on this channel. I mark the boundary and leave the deeper claim there. What is beyond dispute, and what belongs to the union, is narrower and firmer. There is no observer-independent way to extend now across space. The present is local, the interval is universal. And between those two facts lies most of what is strange about living inside Minkowski's geometry. Let me press once more on the vacuum, because the Schlieder result has an implication that took even its discoverers years to fully digest, and it is a genuine piece of net new understanding this subject offers. The theorem says the vacuum is cyclic for any local algebra, that operations in any small region can approximate any global state. But turn it around. It also means the vacuum can never be a state of true local emptiness, in which one region is genuinely independent of the rest. If you could find even one small region whose contents were completely uncorrelated with everything outside it, the theorem would fail. Since the theorem holds, no such region exists. Every patch of empty space is entangled with every other. Emptiness, in quantum field theory, is not the absence of relation. It is a dense web of relation that happens to contain no particles. Picture a still pond at night. It looks empty and inert. But suppose that at every point beneath the surface, the water was silently correlated with the water at every other point, so that the faintest disturbance anywhere was, in a precise mathematical sense, already reflected everywhere. The pond would be still and yet saturated with structure. That is the quantum vacuum the union permits. And microcausality, the light cone written into the operator algebra, is the one law that keeps this saturation from ever becoming a telegraph. What does it mean that the emptiest thing in existence is also the most thoroughly interconnected, and yet perfectly silent? It means the union holds two truths that our intuition insists must conflict, and holds them without strain. The vacuum is woven through with correlation. The vacuum cannot carry a whisper across itself. Both are consequences of the same geometry. Return now to the CMB dipole with the full equation in hand. Because the way our motion imprints itself on the oldest light in the universe is the union operating at the largest scale we can observe. The temperature we see in a given direction on the sky equals the base temperature multiplied by the square root of 1 minus beta squared divided by the quantity 1 minus beta times the cosine of the angle between that direction and our motion. In symbols, the observed temperature, T of theta, equals T naught times the square root of 1 minus beta squared all over 1 minus beta cosine theta. Beta is our speed as a fraction of light speed, about 1,000th. To an excellent approximation, this simplifies to the base temperature times the quantity 1 plus beta cosine theta. The sky ahead of us appears warmer by about a part in 1,000. The sky behind cooler by the same. And the pattern is a smooth dipole across the whole heavens. This is the same Doppler physics that reddens a receding star and blues an approaching one, applied to the afterglow of the early universe. And it is how the Planck satellite pinned our solar system's velocity at 369.82 kilometers per second with an uncertainty of just 11/100ths of a kilometer per second. What does it mean that our motion through the universe is written, faintly but unmistakably, across the entire sky in the temperature of ancient light? It means even the cosmos-spanning backdrop obeys the union's rules. That a boost, the same operation that mixes your desk clock and your ruler, also warms one half of the sky and cools the other. The geometry that governs a lithium ion in a German storage ring governs the light left over from the beginning of everything. And that is precisely why the quasar-dipole anomaly carries the weight it does. If our 370 km per second motion fully explains the warm and cool pattern in the ancient light, then the very same motion should produce a matching lopsidedness in the count of distant galaxies, the same beta, the same direction, the same size. When Nathan Seacrest's team counted over 1.3 million quasars and found a dipole more than twice too large, they were reporting that two measurements of the same motion disagree. Either our motion is larger than the ancient light says, or something other than motion is tilting the distribution of distant matter, or a systematic error is haunting one of the surveys. Each possibility has a champion and a critic, and the reason the field cannot simply pick one is instructive. The samples do not fully agree with each other. Seacrest's infrared quasars and the combined radio surveys show the excess. The independent quare sample does not. When two careful teams measure what should be the same quantity and disagree by more than their stated errors allow, you do not yet know which one is measuring the real river and which one is fighting its own instrument. Picture two survey crews sent to measure the height of the same mountain from opposite valleys. If they return with figures that differ by more than their instrument's rated precision, the responsible conclusion is not the mountain has two heights. It is one crew has an error we have not yet found, and the work is to find it. That is exactly where the cosmic rest frame question sits today. It is not a discovery. It is not a mistake. It is an unresolved disagreement of the most productive kind. And it is being resolved the slow, correct way, one survey at a time. One more strangeness deserves its place before we gather the threads, because it inverts an intuition so basic that most people never examine it. In the geometry you learned as a child, the straight line is the shortest distance between 2 points, and any detour makes the path longer. The union reverses this for paths through time. Among all the ways to travel between two events, one moment here, a later moment there, the path of maximum elapsed proper time is the straight, unaccelerated one. Every detour, every burst of acceleration, every loop out and back shortens the time your own clock records. This is not a paradox, and it is not an illusion. It is the direct arithmetic of the minus sign, and it has been confirmed in every high-precision timing experiment ever performed. The consequence is quietly profound. The path of least effort, coasting, doing nothing, letting inertia carry you, is the path along which the most of your life elapses. What does it mean that the geometry rewards stillness with time and charges acceleration a tax paid in the currency of your own aging? It means the union does not treat all paths as equal, and the way it discriminates is the opposite of everything spatial distance taught you. In space, the wanderer travels farther. In space-time, the wanderer arrives younger. The minus sign is not a technicality. It is the reason the geometry of your life does not behave like the geometry of a map. Gather what all of this establishes, because the accumulation is the argument. A German mathematician in 1908 asked what the equations of moving clocks and rods leave unchanged, and found a single four-dimensional geometry with one flipped sign. a currency that trades space for time under any change of motion, conserving one net quantity. A group of 10 symmetries from which the great conservation laws descend. A cone of causality that orders every cause before its effect for every observer, while permitting harmless disagreement about the distant now. A vacuum entangled through and through, yet forbidden to carry a signal. A family of curved geometries, de Sitter, anti-de Sitter, FLRW, all built on the same minus sign, describing everything from the accelerating cosmos to the theorist's quantum gravity laboratory. A century of experiments, the sapphire resonators to 1 part in a billion billion, the storage ring ions to 9 decimal places, every particle mass reconstructed at every collider, 3 loophole-free tests of the vacuum's entanglement, all confirming that space alone and time alone are not separately real, and their union is. Against that, the alternatives. Preferred foliation theories reaching for the quantum gravity frontier but leaving no fingerprint where we can measure, and a single live cosmic anomaly that would, at most, complicate the global story while leaving the local geometry untouched. Let me bring this exploration to a close. We began with the clock nearest you and the ruler on your desk. 2 instruments your whole life insists belong to 2 separate worlds. We found instead that they draw from one budget. The Lorentz transformation mixes time into space and space into time. The space-time interval is the single number every observer in the universe agrees upon. And Hermann Minkowski, standing in Cologne in 1908, was right that space by itself and time by itself would fade into shadows, leaving only their union with an independent reality. We trace that union through Felix Klein's question about what a group of transformations leaves unchanged, and through the 10 symmetries of the Poincaré group, from which conservation itself descends. We watched lithium ions confirm the mixing to 9 decimal places, and the Higgs boson emerge from the sum of 4 vectors beneath CERN. We felt the razor of the single minus sign, the one that builds the light cone, orders all cause and effect, makes the coasting path the longest lived, and leaves light itself with no elapsed time on its journey. We found the vacuum saturated with entanglement by the Schlieder theorem, yet silenced by microcausality, and watched relativists slice the union apart with the ADM lapse and shift, only to prove the cut was always theirs and never nature's. We pushed the hunt for a preferred frame through the Standard Model extension and the sapphire resonators to 1 part in a billion billion, and found nothing. And we looked hard at the quasar dipole and refused to settle it before the surveys do. Here is what the evidence has shown. Space does not exist on its own, and neither does time. The claim that each is separately real, separately invariant, is not merely incomplete, it is disproven to a precision among the very finest in all of physics. What survives every measurement we know how to make is their union, the interval, the 4-vector, the light cone, the invariant mass. On that question, the one this exploration set out to answer, the verdict is settled, and it is not close. And here is what stays open, named without flinching. Physics can compute every consequence of the minus sign, and cannot yet say why it is there. The tension between our complete local freedom from any preferred frame and the universe's global rest frame is unresolved, riding on an anomaly that may yet dissolve or may yet stand. And whether the union of space and time is the bedrock of reality, or itself emerges from some deeper pre-geometric layer, is a question every instrument we have, all of them working from inside the union, cannot presently reach. That is where the evidence leaves us, certain of the union, honest about its edge. If you have found value in this exploration, consider subscribing. It helps these deep dives reach more of the curious minds that want the mathematics and the honesty together, and it lets me keep making them. So look again at the clock beside you and the ruler on your desk. They were never two things. They are two shadows thrown by one geometry you have lived inside your entire life without ever seeing whole. A single fabric that lets a moment and a place trade places with your every motion, and holds through all of it one number that belongs to no one and binds everyone. Space by itself and time by itself have faded into shadows. Their union has survived every measurement we have ever made. And whether that union is the floor of reality or a floor over a deeper cellar we have not yet learned to open, is the one question worth staying awake for.